All right, we are live. So thanks everyone for tuning in again. This is the fourth episode of my compiler work, where we're working on a new optimization in the compiler called stability, inference, and propagation. Let's see. So I've done a little bit of work since last time, and I just uploaded a patch. So basically, if you looked at the difference between patch set 3 and 4, you'd be able to see some of the things that have changed since last time. I'll put the link to this in the chat if anyone wants to look at it specifically, and I might go over some of the specific changes. So there is the link. I think at this point we will just go ahead and get started. So one of the things I did was I kind of changed how the inference algorithm, let's say, on the front end is going to work. So if you remember last time, we made this like, hey, how's it going, Sky Color? Yeah, happy Friday. I'm just gonna be streaming for a few hours, so we'll see how it goes. So the stability inferencer, this is one of the Kotlin extension points, and it implements declaration checker, which is gonna run over declarations. But I actually want to be able to do the inference from more places. How's it going, Nibian? Yannick asks, will the compiler eventually inline state read access when captured in a lambda, thus registering lower in the hierarchy when possible? What about function arguments? Yeah, so it already does this for the most part. So let's see. I guess one thing to keep in mind is like every composable lambda implements or it is restartable, so we can resume composition from any lambda. So if you, for instance, do something like this, and you say var count by mutable state of, so what happens is, like, if you end up reading count here, so count, what this will do is whenever count changes, it's actually just this lambda that'll end up recomposing. Just because when you execute the read, it just invalidates, or it just subscribes to the nearest composable scope, or restart scope. And in this case, composable lambdas are restart scopes. So let me know if that answers your question. Oh, hey Gurupreet, it's good to see you on here. Yeah, I guess you're about to go to sleep, but so shared element transition tips. Honestly, this is one of the more difficult things right now in Compose. We're actually, I think in order to do shared element transitions in like an ideal way, there's new APIs that we're going to need to introduce, and it's one of the things that we're actively thinking about right now. So I guess for the most part, I feel your pain. Shared element transitions right now in Compose are going to be somewhat difficult. We can talk about like ways that you could kind of accomplish it at the moment, but I think the right way is sort of not yet possible. So you're asking if you read state that value above foo. Yeah, so not sure you got, so like, just to be more clear about the example. So in this case, you know, down here I'm reading count that value, and so if count changed, then just this would get executed. But if I, you know, created something up here, so like if I did this and then read it down here, then whenever count changed, then all of example would change in that case. And so maybe you're asking like if there's some like different way that could work. I'm not sure how you think it could work, but let me know if you think there's something we could do there. Does each composable have an internal key for the compiler to track changes, or is it just subscription to state changes? I'm not quite sure what this is asking, but like at the end of the day, like subscription, or like whenever a state value changes, what happens is like the state subsystem, like it grabs the current invalidation function for like the current scope, which is technically the real primitive here. So you know, you can there's basically an invalidate function, which this is like you can think of it as like a compose intrinsic. And so then whenever I call recompose, it's going to invalidate the scope that this getter was executed at, which in this case will be the example function. And so state is doing that under the hood whenever you read a value. And then what happens is when you write to that value, it essentially calls all of the invalidate functions that are subscribed to that state object. And so in the eyes of like the runtime, it really just understands restartable scopes, which like example is a restartable scope here. So is this like foo composable lambda. Foo itself is probably a restartable scope. Like there's a lot of restartable scopes. So I'm not sure if that answers question or not. Yeah, so basically the question is like, could we like be smart enough to figure out that like temp, even though temp is read up here, it's only used down here. And so like, could you do some control flow analysis to essentially make like just, you know, every read of this would end up down there. I mean, technically you could probably be smart enough to do that, but it might kind of change the behavior in unexpected ways. So like, I'm not sure I would like doing that. Like essentially right here, you're really like, you don't want the compiler to be like too smart, I guess. You know, like if you write this code here, you kind of expect this getter to get executed, and if it doesn't, it's a little bit trippy. I mean, maybe we could do that for like types that we own, like state, but I'm not sure that I would be a fan of that. One of the things that like is nice by like we're trying to promote use of these property delegates. And this is one of the reasons, because kind of by default, this ends up inlining like if you just use this naturally, then it won't really subscribe to it until the scope where it's used. And so like this is you know, code that makes sense. But like if I ended up writing, you know, something like this, I don't know. It would feel weird if we ended up like inlining that all the way. Yeah, so Group Reed says, I hope there's a standard view pager as well in the future. Yeah, there most likely will be. I think it ended up getting cut as a like a P0 feature for 1.0, but you know, when we hit 1.0, that guarantees API stability, but it doesn't prevent us from adding things. And so, you know, a lot more things will be coming, but we want to make sure that what is in Compose at 1.0 is solid. Yeah, if we did it for function arguments, it would be tough. It would defeat a lot of people's expectations, I think. Hi, Rashawn. So, okay, great. So let's go back to the compiler here. So here I have the stability inferencer, which like has this declaration checker and call checker interface, where we're going to be able to run some analysis on like all of the code in the compilation unit. But so what I ended up doing is I refactored this into this stability context thing. And so one reason I did this was I wanted to sometimes on the front end, I'm in like a read and write situation in that I can add metadata to the binding trace, and then other times I'm just in a read-only situation where I can only read metadata that was put in the binding context. And so what I wanted to do is kind of abstract over those two situations and just have this like stability context thing be able to give you the stability of a given thing, and it would use like whatever context you provided it under the hood, and do like this, you know, kind of memoization behavior here. So you call the stability of, and you can call it with like any declaration descriptor, and then I end up handling things independently. So for things like a class descriptor, what I'm doing is I'm memoizing based on the descriptors. So like if we've already done the analysis on this class before, then we'll just grab it and use it. And so then what I do is I grab everything on its member scope, and then I like iterate through each one, and then I like just compute the stability based on that. And so like the stability of the class is sort of like an aggregate of the stability of its members. And so this is like an overload plus, which I'll show you. So I created this stability class. And so one thing to think about is like we have different situations for calculating stability. So there's like some cases where when everything to determine the stability of a given thing is determinable at compile time. So it's like it's certain. We can know for certain that this is either stable or not. And so that's this case. And so in this case, we basically just pass in a Boolean indicating like yes or no. And so this is for things that are going to be in the compilation unit, like probably like simpler things. So you know, so basically a given type like foo, val, bar, int. This is something that we're going to be able to be certain about. And then there's uncertain. So this is something that it might depend on something outside of the compilation unit. So like for instance, if we had foo, val, bar, external type, right? then what's going to happen is that like the stability of foo is going to depend on the stability of the external type. And so that's a stability that we're uncertain about. And so this is something that at the end of the day, we're going to end up generating that like, you know, external type dot stable expression to determine whether or not this is like to determine at runtime if this overall thing is stable. And then we've got like parameter. So this is, for instance, like this. Right. So now the stability of foo is determined by this type parameter t. So like this, it's kind of like uncertain in that whether or not the parameter, like the type of t is stable or not, is uncertain. But in this case, it's determined via a type parameter instead of a type. And so that's one type. And then we've got like combined. So in this case, you know, we've got var b. So in this case, the stability of foo is the combined stability of A and B here. And so this is basically how we can create a chain to calculate the stability. And then I've defined this plus operator, which makes like some Nicholas says, I have no idea what you're talking about, but I'm still watching. Well, I'm sorry to hear that. I'm glad that you're still watching, but let me know if there's something that I can explain better. So I defined this plus operator, which really it creates a combination or a combined stability of two other stabilities, but it makes these optimizations where if one of the two like left or right hand sides of the plus is certain, then the result is just, you know, the other result basically. So like I don't know if that makes sense. So if this is certain and it's stable, then the combined stability of the two is just the stability of the other. And then if the other is certain and then the other is stable, then the combined stability is just the stability of this. And so this is just like a small optimization to like prevent like a bunch of chains that are all stable to like, you know, kind of collapse a little bit. Is plus just like the or operator? Kind of. I mean, so plus in this case, plus actually operates more like the and operator. So like if two things are stable, then it's true. But like if just one of them is stable and the other one's not, then it's not stable. So it's a little bit like the or operator. But it's, you know, yeah. And then I created these static constants for like, you know, stable and unstable, these two certains. And so that's kind of like where I went when I just started digging into like how this could, how we could like kind of start assessing more complicated forms of stability. So let me know if that makes sense to any of you or all of you. I'm pretty happy with where this is going, and a lot of it's going to be kind of adding a lot more logic in here to figure out how to deal with certain things. So let's look at an example here. So one of the interesting cases that we wanted to cover was varfu by mutable state of. And even though this is a writable property, the type of the field is stable, and it's using a delegate. So like in that case, we can like that's still a stable thing, and so we want to make sure that this ends up getting marked as stable. I don't remember if this ended up succeeding or not. We'll see. I think it might. I was just changing around a bunch of stuff before we started here, so. But basically, you can kind of find this code here, where here we get a property descriptor. And so if the delegate field is non-null, then what we have to do is we need to find the actual PSI of the property, and then find the delegate expression, and then we'll get the type of that expression, and then assess the stability of that type. And so that's how that'll work. And so we've got quite a bit of to do in here. Let me also show you, so one of the other things is I created this stable expression function here, which will go through the various types of stability. I didn't end up dealing with these two cases yet, this is kind of the complicated bit. So we'll have to get like the stable property here and figure out how to do that. And then we're also going to deal, what we're going to end up having to do is, like, in the IR backend, we're going to have to probably use like some sort of type substitutor, thing to resolve a type parameter to what it is at that point. And then like if that ends up being the type of some known parameter in scope, then we can use the stability of that parameter to determine it here. And so that'll be some pretty interesting logic once we end up dealing with that. But yeah, so this is incomplete code, but it's, it's a good start. What do you mean by checking the stability of the type, the type of the variable? Yeah, so in this case, so if you haven't watched the first episode, I kind of go over like what stability is, but for a lot of cases, you can just kind of think of it as immutable. And so we're sort of tracking whether or not a given type is mutable or immutable. And that can be just the notion of a type, like a class, like if the class is immutable, or it can be like a value, a given expression. So we're saying, okay, this expression is immutable. And what's nice is that we can end up knowing certain things are immutable, even if their like type in the type system doesn't guarantee it. And like, so that's, for instance, one of the things that we can do is, we can say, so in this case, list is of type list of string, and there's no guarantee by the type system that list of string is immutable. But we can create a more refined sense of that because we know where this value came from, because it came from this list of function, which is going to return an implementation of list that is sort of known to be immutable. And there's like interesting things like that we can do So that's one of the things here. Thought it was Jake Gyllenhaal that was coding for a brief moment. Yeah, I get that a lot. Okay. So this ended up passing, which is pretty cool. So just to like kind of prove what's happening here. So this ended up getting marked as stable, but for instance, this should not get marked as stable. Oh, whoops. And the way that works is here, and so we went through that already. But like, if there's no delegate, then what it's going to do is it's going to see, okay, it's a var, and there is backing field to it. So then in this case it's not stable. And then otherwise, so if it's a val, then the stability of the property is really just whether or not the type itself is stable. Do you think we could have something like an icon in the gutter to indicate that a class was inferred as stable? Yeah, I do. So this is one of the reasons that I wanted to make sure that this analysis happens on the front end of the compiler, so that it can run in the IDE, and potentially we can surface that to the user in some ways. So it's good question. I'm not sure if a gutter icon is the best way to do that, but it is one possible way that we'll do that. So, yeah. Okay. I'm gonna like just start filling some of this in, but we'll probably want to head over to some different parts first. So yeah, so here's when I changed this to varfu, what I got was it said it expected it to be stable, but it found it to be certain unstable, and so that's exactly what we expect. So that's good. So that's like working. Okay, so module descriptor here, like understanding the stability of a module is kind of nonsensical. So I'm just returning unstable. Maybe I'll add a comment to sort of that effect here. Aren't really. Okay. So let's try out it's kind of interesting when we start doing some of these other things, like what analysis makes sense. Like some of these things maybe we shouldn't even be analyzing. I'm not sure yet though, because we're gonna have to start analyzing some expressions. So parameters you can't really mutate them, and so this is nice. This kind of inherently is like some level of stability, but it really just depends on the type. So what we're probably going to do here is return stability of descriptor dot type, and then that's like probably enough. And because this isn't really doing any meaningful work, I'm not going to memoize this because that's just wasting memory at that point, I think. Can a pointer be a parameter? What do you mean by that exactly? Like what do you mean by pointer? And then Rashawn asks, why does the function body, why is it wrapped in a memoized call? So this is like just one of the things that I'm doing to like as we go through the type system, like the whole, as we analyze different things, we might ask for the stability of a given descriptor many times, and so we don't want to duplicate that analysis like all the time. And so what I'm doing is I've created this memoize function, which it uses this binding context and binding trace that is like a big part of the like the Kotlin front end, and it's basically like, you can think of it as like a typed map, and so I can save information there. And so basically what I'm doing is based on the key, I can grab and ask, okay, did we already check this? If we did, then just return that value. Otherwise, run this code to figure it out. And once you figure it out, then record it if we have the ability to record it, so that the next time this question gets asked, we'll have saved that analysis. And so I'm just doing that in a lot of these places to save that work. Yeah, so Skycolor, you can't really pass a pointer to a local variable, like a local piece of memory or anything like that. Like, so Kotlin doesn't really have that notion. You can have, like, JVM has like these like pointer objects, but in that case, like, they just kind of follow the same rules as other objects, and they just have a piece of memory that they're pointing to. And so our analysis wouldn't be any different for that. Okay. Yeah, so I shouldn't memoize any of these things that aren't like doing other work here. So not. Well, actually, this one's gonna do some more work, so this will be interesting. We'll play around with this a little bit. So I wonder, I think, so I wonder if we should do more here. Like, basically, we might want to handle some things, especially if there are non-default getters and setters. Yeah, so will stability and will we infer the stability of Java classes? Basically, the answer is no. Like at the moment, really what we're doing is we're only inferring the stability of classes that are in the compilation unit. So that is, you know, things that are being compiled by Kotlin with the Compose compiler plugin. But what we're also doing is that we're creating a sort of encoding of this information to be able to have that stored metadata kind of be communicated across module boundaries, but only to other compilation units that were compiled with our compiler. So a Java class won't fall into this category, but one of the things that we're going to be doing is we're going to be allowing you to pass to the compiler some sort of a configuration. I haven't figured out all the details yet, but some way to configure essentially telling this inference engine to treat certain types as stable, like regardless of whether they are technically or not. Like it'll be a way for you to force certain probably like fully qualified names like as stable. And so this will help, like if you, like for instance, if you are writing some sort of a code generator, like let's say you've got, you know, some internal infrastructure that generates all of these Java classes based on like, you know, some database schema or something like that. And so when you do that, one thing that you could do, like if you happen to know that all of these classes are used like technically in like an immutable fashion, like whenever the user is using these, like they're not going to mutate any of the data in them. And so what you could do is, like if you own this infrastructure, you could pipe into the Kotlin compiler like a flag that basically, you know, designates all of these classes as stable, and then we would treat it that way. And so that's sort of like our answer to this question, like the more nuanced answer to that question. But by default, we won't really be dealing with Java classes or attempting to do any inference of classes that are defined outside of this compilation unit. Cyrus or Cyros, I don't know how to pronounce it, but he says, they say, I can't help but to notice your background soundtracks are amazing. Yeah, it seems like a lot of people are liking the music choice. I'm using this service called Pretzel Rocks, which is like a service kind of built for streamers, which lets you, basically all the music is like copyright free, so there's no risk of like DMCA takedown or anything like that. And it's actually really nice because you can specify if you want like instrumental only, and they have like a bunch of different tracks that are like different categories. Like, so I just started listening to the chill category and started creating my own playlist of stuff that I just felt like was, you know, just chill and mellow and like good background music. So now I'm using it like even when I'm not streaming. I think it's great. Okay. So I'm gonna put a to-do here just to make sure that I don't forget it. To make sure that we look at getters, setters when they are there. I'm actually not sure that it matters. Like, I mean, so there's some level of correctness that we need to, you know, kind of think about here. Like, it's unclear technically how correct we want to be, but let me like show you some examples. For instance, so let's say we had something like this. know, this is like kind of a silly example, but you know, print in getter return field. So I could write code like this, and it's from a like a truly academic perspective, like calling this getter has real side effects. Like it's printing to standard out basically, and that's like an observable side effect, and like there's some question about whether or not that should obey the stable property or not, or the stable contract. We're going to probably like lean into this case and say like, yes, it does. And the kind of the idea is like, am I able, like realistically, am I able to use an instance of bar in a composable and like, you know, conditionally render some UI based on it? And do I reasonably expect that UI to change if I called it again? Like, would it be reasonable to expect that UI would change? And like at this point, you know, the only like public thing that you can do on an instance of bar is get a foo, and it's going to return the same value. It'll always return the same value. And so if we pass in the same bar to a composable function, we should expect that the result of that composable function is going to be the same. Even though, like, I don't know. I mean, you could write some really gnarly code that maybe would make it not, like if you looked at like standard out and stuff like this. But I think the general idea is that like the public API of bar is something that there's no observable way for it to change if you passed in the same value from the last time that you passed it in. And so that's kind of the idea that we're going for. And so one way to think about this, I guess, is like, if oh, and another thing is that like we tend to in compose, like the optimizations that we've taken, generally speaking, is that like the escape hatch is to reach for global state. So like you know, global thing, like there's maybe something I can do here that like that's not necessarily something that the compose compiler is going to understand. So yeah, so SkyColorX asks if the getter would also call an external service like an API, would that automatically be unstable? So that's like kind of the question I'm trying to answer here. It's like, so here's the thing. So like if the getter did something like this, some global API dot return foo, right? Like let's say it did this. So there's no backing field. I think what we're probably going to do is we're probably going to say that bar in this case is still stable, even though some global API, like this is clearly not, like this would kind of defeat our optimizations, or like it might produce behavior that is weird. But here's the thing is like, if you did something like this, global API, you know, API equals, you know, or let's say it's like this. And then, you know, your code did this. The idea is that like it doesn't really matter what foo does here. Like at this point, you've got this unstable type as one of the backing fields of bar. And I think what we will say is that in this case, this type is not stable. Like the public API of foo might kind of look stable, right? Like 'cause all you can do is grab this int here, but But like, just because this is a read-only property doesn't mean that like there's not some mutation happening under the hood. And in general, the idea is that like if the class has access to an unstable type, then that mutation could be occurring. But I think that the line that we're going to say is like okay to cross is accessing globals, or like basically accessing stuff through like something other than a closure, right? So like so basically this is a way that you could cheat potentially. I'm not 100% sure that we like that answer, but it's hard because I think that like what would happen, like as soon as we say that this is cheating, then like we also kind of have to say like this is also bad, and it's kind of a bummer if like all of these things end up destroying the stability of all your types and stuff like that. And so we've generally tried to be careful about what exceptions we do have, but I think that like these might be okay. What if the getter would contain a try catch and then something that returns a stable thing? Yeah, so you're saying like, you know, some calculation, catch, you know, whatever. You know, in this case, it returns 0. Like, so this is fine. I guess this is kind of what I'm saying is that I think what we're probably going to do is that the body of the getter doesn't really matter. Its return type matters. And it's like we're not really the stability of bar is like the real question here. And at the end of the day is like we're saying if bar has any fields that have unstable types, then that's when we're kind of saying, okay, this is no longer stable. And so the try catch here doesn't really matter. Excuse me. Okay. Yeah, I think that's the line that we're going to be balancing on, but that's basically what we'll be saying. So in this case, I'm not sure that I need to look at the getters and setters here. I think at this point the type is enough because we'll end up looking at the other types of the class and the fields to like determine if the overall type is stable, which should tell us whether or not the getters sort of had access to any sort of unstable mutation, except for in the global context, which we're just saying, you know, we're not worrying about that. So, I mean, this gets to like kind of an interesting question about, like, let's say we've got, you know, we've got some obviously mutable class here, you know, and then we've got some other class which doesn't have any unstable types on as its fields, but it has like a, you know, it's like a CounterFactory, right? And in this case, the CounterFactory, you know, it's able to make a counter, which is unstable, but the factory itself, I think, ought to be considered stable. Trying to make sure I agree with that statement. I don't know. I think I do. I'll need to think more about it. I mean, these are the things that we want to be careful about, but I think so. And so then it gets like kind of weird, like, because this, you know, the stability of the function descriptor is like, it's like, okay, well, actually, you know, is it stable? And then so I think we need to I think we might need to have a separate concept from stability of purity. I don't know. I'll be thinking about this more. Okay. So this is kind of interesting. Let's what I kind of want to do is like let's try and get the whole pipeline working, right? And so these tests just run the front end, and so we want to work the back end a little bit here. And to do that, let's say I'm gonna just duplicate these tests here. Oh, actually, I already have a thing, don't I? Yeah. There's like a stability transform test or something. Class stability transform tests. Although that's specifically about the class transform. So, well, all right, I'm gonna open that file, but then I also want, so the class stability transform is really just about taking a class and then adding that synthetic field on it if we need to. So what I want to do is I want to create another test that's really just about composable functions and the skipping logic around stability. Composable stability, let's call it stability propagation transform tests, because that's really what we mean when we say stability propagation, is like how in composable functions we pass the stability along. All right, so I'm going to keep the first test here and then just delete all of these. So this like just adds in, yeah, this is fine. I'll rename this though. Can there be composable functions inside of a class? Yes. They can be methods, or anywhere a function can be, really. A composable function can be. Will it work with an interface? That's a really good question. So interfaces are interesting. What we're gonna do is, where is that test? Stability inference test. Okay, so let's say, so their interfaces are gonna be in one of two categories. So an interface will either guarantee that its subtype is, like, any implementation of it is unstable, or do nothing, like or we don't know. And so, like, for instance, the list interface, right? This is an interface where we aren't really sure whether or not, like, it means an implementation of it is stable or not. We can have stable lists, and so it doesn't indicate one or the other. But we might have something. Actually, it might not, maybe it doesn't even do this. So if we have something like this, well, okay. No, yeah. Like, we could say, if an interface is like this, we could say that foo now guarantees that any implementations of it are unstable, but actually we kind of can't because of this, right? We can implement this mutable property by means of a stable state object, for instance. So I think that we can't guarantee, like, interfaces will always just be sort of uncertain. We won't know if their implementations are stable or not. But I think that what we will allow is that you'll be able to say that a given interface is required to be stable. So we'll say that any implementation of foo is stable by definition because it's part of the contract of being a foo. And so one like instance of that is the state interface, right? State in Compose is an interface, but we've marked it as stable. And you know, it's it sort of looks exactly like this, right? So the expectation is that if you implement state, then you are following the stable contract. And I think that this is probably what we'll do, is so that, like, the only useful thing you can do with an interface is, like, so you can do nothing, in which case it says nothing then about the stability of its subtypes, or you can mark it as stable explicitly, and then that means that, like, this is now part of my contract. And so I think those will be the two things that we'll allow. Okay. So what I want to do here is I want to have a stable type. So this is inferred as stable. And then what I want to do is I want to call another composable. And so this will be A, and it'll accept any. So there's nothing in the body of A that, like, tells us that X X is going to be stable. It can be either. So any is, you know, some base class, and it doesn't say anything about the stability of any of its subtypes. And so in this case, if we pass in, so like basically we can do this. So I want to do that, and then I also want to do this, and I want to see what the two things that it does are. And then, well, actually, I'll do a third thing. All right. It's conceivable that at some point we might realize that passing in a constructed foo here is, if foo doesn't have like an equals function or something, that like this would never compare true. So then we might as well just not compare anything else. And so maybe we would do something like that, but we don't right now. Does stability correspond to immutability? Yes, they're very closely related. So anything that is immutable is also stable, but there are some things that are stable that aren't immutable. Okay, so let's try this. This isn't going to do anything right now because we're not really tracking, or we don't have the code that does the right thing here. So so variable, just doing that. Oh, I can't do that? I thought I could. You're asking for an example of something that's stable but not immutable? If so, state is one of those examples. So immutable state of returns a state object, and as far as you're concerned, it's immutable, but it obeys the stable contract, which, you know, is kind of like us cheating, but it basically it allows us to say that because state communicates its mutations with compose, that it obeys this stable contract. No value for parameter. Oh, I need to pass in something to foo here. Makes sense. Okay. Yeah. Oh, I need to import remember. Fair enough. Why do my tests look like comments? Well, so I feel like they don't look like comments, but they look like strings, because they are. So basically the test that I'm writing is like you pass in these strings that are essentially valid source code, and then that's sort of how the test infrastructure works. It would be nice. Someone told me there's like a way, I forget what it was, but there's like a way to make to basically tell IntelliJ that like this is source code and like it's Kotlin code, and then it would like syntax highlight it properly. I don't remember how to do that, so if anyone knows, let me know. We can give it a shot. Okay. So this is what the test spit out. And so, you know, this first one is kind of working appropriately. Like, it's basically saying, you know, take all the metadata from that was passed into foo and just pass it in to A directly. So that works. But these other ones aren't working correctly. We see that they're returning, or they're passing in 0 for the changed parameter. You can prompt the options in the string and select the language. Yeah. I don't see anything for that. Yeah, I built the test infrastructure to like work on our transforms. Yeah. You have to annotate the source string parameter with interesting. So if I do, this will be really cool if it works. Org.intellij. Maybe the type here. Org. Lang.annotations, language, Kotlin. Okay, if this works, it'd be super cool. What is this? So annotation is not applicable to target type usage. Okay, so maybe to the parameter. Yeah, aha, cool. It works. That's dope. All right, let's try. What? If I do the transformed, it'll probably freak out. Yeah, kind of. Maybe I won't do the transformed, but this is really cool. Okay, cool. Thank you. Who told me that? Evian. Yeah, thank you, Evian. An immutable collection map with immutable elements, will it be considered stable? So yeah, Sergey, this is one of the goals of this this optimization, is that if you have an immutable like list or something, and the element type is immutable, then like we'll consider that stable. And that's one of the more important use cases for this optimization. Okay. So basically, let's talk about what we want this to be. At this point, like, you know, foo is getting past Foo's getting past A is getting past an immutable type, or a stable type. And so the type of this argument is foo, and we can determine that foo is stable. And so what we want to pass in here is actually like a constant here. So we want to 1 0 0 0. So basically this 1 0 0 is the metadata that we want to pass in for this expression here, which is to say that its type is stable, but we don't know if it's certain or not, if that makes sense. And then we basically want to return the same thing for this. What's interesting though is that we could actually pass in something more extreme for this. We could actually pass in that, which is to say that because it's remembered, we actually know that it'll never change. And so we could not only pass in that the type is stable, but we could pass in that the value itself is static. And so then we won't even bother comparing it. And so this would be cool if we did that. I actually have some of that code in place, but I don't remember if it'll be smart enough to catch this particular case. But we can look into that later. But I think for now, let's just make sure that it passes in static, right? Or not static, stable. So we'll do that. And I guess it's important to note that, like, so this is the case here because foo is in our compilation unit, and so its stability is certain. Like, we know for sure whether it's stable or not. If it was outside of our compilation unit, what we would instead do is we would say something like this, and that's because then at that point the stability of foo is unstable, or it's uncertain, and so we need to resolve that like at runtime. And so we would do that in this way. And so we'll have to test out both cases, but for now, let's just focus on the local case, which is going to be this constant here. Okay. So to do that, we're gonna go to the function body transformer. And we have this like, what's it called? It's like build metadata or something like that. Build changed params for call. All right, so this is what we want. Well, and actually this one maybe too. So that's the param meta. Where is this used? Okay. So here, this is like pretty close to what we want. So here, what we're saying, we have this param meta object, and we're populating the metadata here. So param meta. Okay. Here's where we probably want to add this stability. I'm gonna set it to null first. So we used to be, we like enumerated these cases before. So it's like, it's either guaranteed to be stable. And so this is like the, when it's stability.certain, and then it's guaranteed not to be stable. So this is stability.certain with stable false, and then it might be stable. And so we've this third case is like kind of an important one, and stability now encodes a lot of the different situations of might be, right? So now this type is enough to like encode all of this information, whereas like a simple enum was not like expressive enough before. Okay, and so then this is the expression of the so this is the expression that we get. I just realized some flaws in some of my plan, but we can hook this up a little bit. So we'll be able to improve this at some point with the stability analysis that we have, but I'm not going to do that yet. So we want to say so a real simple thing that we can do is we can just say to Kotlin type dot get stability. But this is only taking into account the type, not the actual expression. And so we might want to do more with that at some point. I need to figure out what makes sense there, because we have an IR expression, which is something that on the front end, doesn't exist. So I'm not sure the right thing there. But if we just, all right, so now we're taking this param meta, and then we're gonna build that expression from it. Oops, all right. So we're building the change params for the call. I don't want that. All right. So here's what we do. We look at all of this, and we construct some expression which is like an anded and ored, int across all these things. Love it's always 0. So what do? I loop through each param. Bits for slot. I see. Okay. So for this expression, I have two things that I'm building. One is like this starting constant. So if it's known at compile time, like the number that we're going to be passing in, then we at compile time build up this like constant int. But then we have a bunch of expressions as well that we're also building up. So if the change expression for that parameter is dynamic in some way, then it goes into the or expressions, and then we combine them at the end. So what we can do here is we can we can tack on some of this stuff. So if meta.stability, I wonder, okay, so we should not make this nullable. We should just start off like stability to unstable or something is like the default. And then when we set it, it'll be something else. Yeah, okay. So okay. Here we can say meta.stability well, let's save it so that we can smartcast. And so if it's certain, okay. So if we know that it's unstable, we can kind of just pass in 0 here. Interesting. So that's like kind of an optimization that, well, but we want to send in, we do kind of want to send in the other metadata, even though this, okay. So, if stability actually, let's do this. So stability dot known unstable. So if we know for sure that that the type isn't going to be stable, then we can just we can just go to the next index here. So there's nothing to do. No point in passing it on. Okay. So here I'll return for each index. If stability dot known stable, then we can just update this bitmask constant, right? Equals bitmask constant or stability bits dot stable dot bits for slot. Okay. So we've just made this particular parameter, we've indicated that it's stable. It's always going to be stable. There's no expression that we need to generate. Otherwise, what we want to do is we're going to add to the or expressions. It's interesting though, because we're kind of duplicating some work here. Let me think about that more later. Let's just see what happens when we add this. Some mask. Okay, so that's from the mask. We don't necessarily want to do that. I actually think this else case, it's more complicated. We're not really prepared to do this yet. Deal with this more complicated case. But I think this will kind of work for the example that we have. So let's give it a try. Okay, so that did not work. I'm getting 0 for everything. And actually, even worse, somehow this ended up being 0 as well. So we messed something up. Oh, it's probably because of this. Because if it's known unstable, then I'm skipping that parameter. But I wonder, so why did it show up as known unstable? Oh. That's why. Because that's what I returned. So if we go, where is it? Yeah, here. So we're actually not dealing with this case yet. So when we ask for the stability of a type, we go through some like known situations where it's like we've already been knowing that it's stable. I'm gonna change this to stability of type dot type parameter. Wait, what did I just have? Oh, okay. Okay, so if we get all the way down here, what we actually need to do is we need to get the stability of the class that the type represents potentially. So so if the type is a simple type, Constructor. Arguments. Interesting. Okay. Is dynamic, is flexible. Oh, as simple type. I wonder, so what does simple type buy me again? So I'm not actually sure. Let's see, constructor dot declaration descriptor. So if we go in here, let's just say we can get the classifier here, and then if classifier isn't null, we're going to return the stability of the classifier. Else we'll return unstable, because we're in a weird situation then. But I think what I'm gonna need to do, deal with type parameters. But we'll see what, because we don't have that in the current case. So let's just try this first. And then we're gonna have to deal. Well, no, we'll do that elsewhere. As far as dealing with like local versus external types. Okay, let's try that. Oh, yeah. It wasn't supposed to be there. All right, so for this whole class descriptor thing, what we'll want to do at some point is determine if it's external or not. Okay. Interesting. Okay, so this this partially worked. Okay. In this test, what we ended up getting was this. And so this is good in some ways because it it tells us now that foo didn't get marked as known unstable because we ended up getting this extra skipping logic generated here, but we're still passing in 0 here, which we don't want to do. So this should still be that, and that should be that. So excuse me. I think what we want to do, let's set some breakpoints. For one, we should see what's happening here, and then also I want to understand this. So get stability. Let's see what we get out of that. We should end up changing. We use this in places that we shouldn't. So build statements for skipping this parameter. I see. So we should probably fix this. And then what does this do? Okay, well, we haven't changed this yet. This is for composable lambdas, but we'll do that. Okay, where are we? So we are calling get stability of type foo, which makes sense. And we're asking if it's known unstable. So we shouldn't hit this. We should end up hitting this. Yeah, okay. Which is good. And then now we're in populate param metadata. The arg.type is foo, which is good. So this should also return that it is certain stable. Okay, that's what we wanted. And then inside here, so at this point it's going to be known stable. So we should hit this. Yeah. All right. Okay, and then do I do something here? That's weird. So static is false, is certain. So is certain is true. So okay, so this is when we're passing in x. So that kind of makes sense. So we should end up down here again. I want to see what we end up doing here. Okay. Oh. Wait a minute. So is that right? So yeah, I guess so stable is 0. So we should be expecting to pass in 0. It's when it's unstable that we'll be passing in something else. Oh, okay. I forgot about that. I forgot that I chose 0 for stable. Jafar asks, after using compose instead of XML, will navigation components be useless? I don't think so. I mean, navigation is still like an important thing, and you know, it's not necessarily easy, and like you'll want to handle navigation properly for user experience and being able to navigate to different screens and all that stuff. So the way that you use navigation might end up looking a little different in terms of the code that you write, but yeah, it's still an important thing. So I'm not sure, maybe I'm missing the point of your question. Okay, so realistically here, what we want is we want to make sure that unstable is propagated here. Oh, unknown. Yeah, okay, that's fine. Unknown. And then since I'm gonna rename this because I don't unstable. I think we're handling like the uncertainty in other areas. So, but this is we're certain that it's unstable, so we're gonna call it that. So if it's unstable, then there's 0 point in propagating the other information for that parameter. But there might be some value in propagating the metadata for the other parameters, because even though the function you're calling won't skip, it's possible that the information will be passed selectively into other functions that will skip. So we're gonna continue passing the other bits of metadata. If it is known to be unstable, there's no purpose in propagating any additional metadata for this parameter. But we still want to propagate the other ones. Okay. Hey Alex, how's it going? Okay, so in this case, the 0 that we were seeing in the transform test was actually what we wanted. I just kind of forgot that. So 0 here is expected, as it is here. And okay, so ooh, I just remembered another thing. So in the class descriptor, so if it is not final, then it's not certain. Do we want to do that? Then its stability isn't certain. Figure out best way to handle that. Okay. So let's make another test. So test passing local known stable. And then we'll create another test that's a known unstable. Local known unstable. So in this case, we can say varfu and do the same thing. And let's see what we get. So I expect in this case we'll get, so we won't have this skipping logic, and then we'll get the OB100 constant there and here. And in this case, I wonder if I think this will avoid passing in the whole parameter here. So let's see. All right, cool. Yeah, this looks right. So get something like this. And so in this case, we know that the parameter x is guaranteed to be unstable. So we don't bother propagating any information. We don't even, we don't generate any skipping logic at the top. And then all we do is we just pass down below us. We say, listen, this parameter is unstable. Don't bother doing anything with it. And then we do the same thing for the other two, because the parameter type then is locally known to be foo. So an interesting test here is going to be like basically when ensuring that we don't do this when it's uncertain instead of known unstable. Hey Joe NRV, good to see you here again. Okay. So this is a pretty good start. We're gonna try and get what should we do next? Like I think getting some of the external types set up is going to be a really big challenge. Because we're gonna have to find the synthetic stable parameter in those cases, and so I think like this, like as far as the local compilation unit is concerned, I think we have everything piped, like wired up to get that working, but it's the cross module bit that's going to be difficult. So but actually there's I also want to I want to figure out how to deal with expressions versus types. And that I don't have to, because I'm going to have to build some slightly new infrastructure for the cross module stuff. So let's try that first. So list might be a good example of this. Although that's going to deal with type parameters. So maybe we just do something more specific here. What would be, well, no, let's just do it. So we'll do the list of example. So we'll keep this test list of marked as stable. So we've got our example, or actually, okay. Let's just real basic here. List of, you know, A. So no type parameters in the composable functions. And the idea is that we're going to analyze this expression, and we're going to have some special handling for some functions such as list of that will allow us to determine that type, or that expression, that value is stable, even though the type isn't necessarily. So I honestly do not know yet how we're gonna do this. So let's see what's available to us. In the function body transformer, or we're gonna say populate ram meta. So at this point we have the argument, which is an IR expression. And what we need to do is we need to utilize the analysis that we did on the front end to understand this expression in particular, which is going to be tough. So arg here is an IR call. So I mean we can get the descriptor, but we're trying not to, right? We're trying to avoid using the descriptors on the back end. So, like, I wonder if there's some way that we can keep using the type here, but like, we've got this plugin, which is going to run unresolved calls. And what can I do here? Check type, check receiver. But all I can do there is issue a diagnostic, save something. So that's not going to help me. What can I do for the expression? I'm not sure there's a way I can get around this. I mean, for the type, like, we can't add an annotation to the type for this, for like an arbitrary call. So yeah, and I mean, like, there's, so like, for instance, we use find PSI in a few places. Where do we use it? So we use find PSI here in the binding context. I mean, this is not great. I mean, this is really cheating, right? I think. But it does let us use the binding context. Well, yeah. And I mean, they're deprecating this. Which actually I'm already using. I wonder if I should just get this working first, or if I should really figure out a different path. Because this is pretty important. It's important for us to be able to differentiate based on the expression itself. So we might need to, I mean, Like, I think the only way around using the binding context is then tapping into the PSI to IR in some way, which I also don't think we want to do. Let me see. We've got this inferencer. Where is this? So, non-stable extension points. Not really sure. There's not a good way to do this. I'm gonna try to get something working, and I might reach out to some folks to see if they have some better ideas. Yeah. So what we can do is this. Populate param meta. So here we are. What I might do is, let's say, so we can have like a fun IR expression dot get stability. And so what this is going to do is fire this dot find. What did I do to find PSI? Oh, that's for a descriptor. Find PSI. Yeah, this is going to be really gross. But we'll give it a shot. So in this is IR call. Descriptor symbol descriptor. Equals, and then what I'm gonna do is like kind of the same thing that we do up here. If PSI is not null, then we're gonna get the stability of that. So this is gonna return a PSI element. think that might be all right. Hello, Wasif Akhtar. Nice to see you in here. Okay, so we need basically to create this overload, which I'm not really happy about this overload, but you know, it's kind of interesting. So we get the descriptor, but I wonder if this descriptor is like, all right. We'll have to see what this, because this is, so list of has a type argument and it's resolved at this point, but I don't think it will be for the descriptor. So let's see what that returns here. So let's build this function. And we could pass in the descriptor, but the descriptor is not enough. We need the PSI. Okay, so let's try this. I'm not sure if I want to memorize it yet. Let's just return stable here, which is kind of gross, but and then we'll see what's there. So that gives us that. We can return this. And then like as a fallback at the very end, we can just say, you know, if we haven't returned anything yet, let's return the type dot get stability. So we fall back to just the stability of the type itself, which is kind of what we're doing today. So this will be a special case, which list of will fall into. And oh, but you know, all right, I'm not sure if it will or not, because it's not, there's no PSI for the list of, there's only the PSI for the call itself. So this might be wrong. Am I testing the right thing? Test list of, yeah. All right, let's see what this does. Where are we? We're here. Oh, but we're not doing, all right. So what we want to do is this. Yeah. And this isn't that, so, I mean, at the end of the day, we could start, we could have the expression inference. We could do some of that just using the IR, which is similar to how we do is static here. We like look through some of this, and so then basically we can determine stability based on like, you know, building up some set of stability based on the types of functions and arguments. Having some functions special cased. I'm not really. I don't like that. Because it means that we wouldn't be able to ever expose that to the front end if we wanted to. All right. So let's dive into this. Okay, yeah, so the descriptor for this call ends up as null because it's list of. That's rough. So I don't know if there's, I mean, there's not really a mechanism for us to get from this call to the like PSI of that call. All right. Let's see. Sergey asks, as per documentation, a composable function might execute within a pool of background threads during recomposition, which may cause unexpected behavior race condition. Oh, this is an, is it possible for the lint compiler to check if your composable function has side effects and throw you a warning? So yeah, it's possible. We aren't doing it yet, but we'll probably ramp up on linting as time goes on. Like right now, we're focused more on like getting the API how we want it to be, and then you know it relates to like any other developer tooling that we build, but we might start to try and detect kind of like known bad patterns. So if we see something that's like obviously a side effect that you probably shouldn't be calling in a composable function, we might let you know that, you know, hey, that's probably not a good idea. I don't think we'll ever treat such a thing as like a compiler error or anything like that. Like this would be in the realm of, you know, warnings, like trying to help you, but not necessarily like if you really know what you're doing, then you know you can kind of do whatever you want in a composable function, and we're not going to stop you as long as it's valid code. So yeah, we can do that, and we probably will to some degree. Okay, I think at this point, so I'm kind of hungry. It's almost 1. We've been going for a little over 2 hours now, 2 hours and 16 minutes. So I think I'm gonna stop here. This is a little bit tricky. I'm gonna need to figure out how we analyze expressions, and we might need to do some of that analysis on the back end, which I'm kind of bummed about, but maybe it makes sense. Yeah, I don't know. So I might talk with some folks about this and see what they think. If any of you have any ideas, let me know. But we will, I mean, so I'll be continuing to work on this on my own, but the next stream for this will end up being next Wednesday, but I'm going to be streaming on Sunday and Monday with the composed dog fooding stuff. So if you're interested in that, then please come by and check it out. As always, thanks everyone for your support and coming by. Hope it was useful, and I'll see you next time. Cheers.